All right, chapter 4 is about reactions. It's titled Reactions and Aqueous Solutions, but really it should just be titled Reactions, Aqueous Solutions, and some other stuff that we need to learn but don't have a good spot for. So we're first going to start talking about solution terms. And these are terms that you just have to sort of memorize and know the definitions of. So first, let's talk about solutes. A solute is something that dissolves into a solvent. Technically, when we deal with solute solvent, the solvent is the portion that is in greater amount than the solute. So, for example, when you put a lot of sugar in your coffee, somebody goes, ha ha ha, have a little coffee with your sugar. Well, theoretically, if you add enough sugar, it will become the solvent, and the coffee in the water would become solutes. And that brings us to concentration. Now, there are many different concentration units we can talk about when we're dealing with solutions. There's the mass to volume percentage. There's the mass to mass percentage. There's a volume to volume percentage. There's molarity, molality, all sorts of different things. So, the one we're going to deal with the most in this class, though, is molarity. Why molarity? Because it's got moles. And why do we like moles? Because we can do stoichiometry with moles. So molarity, capital M, is the number of moles of solute per liter of solution. SOL apostrophe N is solution. So moles of solute per liter of solution. Whenever you see that big M, that's what that means. Now I also tell you, whenever you see that big M, just cross it out and write moles of solute per liter of solution, because this is going to be useful when we do our solution stoich. Okay? So when we do stoichiometry, that's going to be very important. Now, we can also talk about concentration in some less mathematical terms, like dilute or concentrated. Dilute is when you have a small amount of solute. What concentrates something dilute? Well, that's all about your perception. 1 gram of sugar in a gallon of water would be dilute. You wouldn't really notice that it was there. It's just completely arbitrary. Same with concentrated. Now, if you had 1 gram of sugar in 1 milliliter of water, well, that would be quite concentrated. But it is all about your perception. Anyway, enough about concentrated and dilute. And then we have the word aqueous. Aqueous means in water. That means that the solvent is water. Okay? So here we have 2 solutions of potassium permanganate, aqueous solutions. Now I like potassium permanganate because it's really a beautiful purple color. Now I can tell you from experience that obviously the one on the right is more dilute than the one on the left because it's got a lighter color. However, they are both very dilute solutions because potassium permanganate is so brilliantly colored that a concentrated solution of potassium permanganate would be too dark to even realize that you could get light through it. Anyway, let's talk about the solution process. Now, the solution process is going to be different depending upon your solute. If you have an ionic solute or a molecular solute, the solution process is slightly different. So let's talk about ionic solutes first, because that's going to be important mostly for our reactions. So soluble ionic solutes are going to dissociate into solvent-separated ions, which means that they're going to break apart. They're no longer going to be an ionic compound. They're going to be separated by the solvent molecules. Okay? Now, this charge separation allows a solution that contains a soluble ionic compound to conduct electricity. And we call these types of solutions electrolytes. Electrolytes come in different types. We have strong, weak, and non. Now, strong electrolytes occur when we have a complete dissociation of ions in solution. Okay, so these are going to be our soluble ionic compounds, our strong acids, and our strong bases. These guys are going to conduct electricity well, as you see in picture C here. Weak electrolytes are going to be from incomplete dissociation. This is when we have only something that's slightly soluble ionic compound or a weak acid or a weak base. In other words, there is dissociation of ions. However, the majority of our solutes remain together. In other words, they are not separated into ions. For our weak acids and bases, what we're talking about is these are going to remain as molecules more than they are ions. Now, non-electrolytes do not dissociate at all. These are mostly molecular compounds that are not weak acids and bases. So, the molecular compounds, such as sugar, they don't break up into ions because they're not ionic. So molecules don't break up. So I can't put sugar into water and expect it to conduct electricity. I can't put ethanol into water and expect it to conduct electricity. So these are our non-electrolytes. They do not break apart into ions because they are not ions. They are not going to be capable of passing charge, which is the passage of electricity. At this point, let's talk about strong acids. Strong acids are going to be, of these 7, they're going to be either hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, or chloric. If you have an acid and it is one of these 7, then it is strong. Any other acid that you may encounter must then be weak. Our strong bases are going to be the hydroxides of group 1A, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. So these are the group 1A hydroxides. And the heavy group 2s. These are calcium hydroxide, strontium hydroxide, and barium hydroxide. These guys are all strong. If you have any other hydroxide, it must be a weak base. Okay, any other hydroxide is a weak base. Any other base you encounter must be a weak base. These are our only strong bases. Now, the solvation process when we have ions is very particular. Water is a great solvent because it is polar, meaning it has a separation of charges. You can see here on this picture that there is a slight negative charge and a slight positive charge to the water molecule. These white balls are hydrogens. The red ball is the oxygen. You can see the oxygen is a little bit negative. That's what we have with the lowercase delta minus. The lowercase delta, that guy, means a little bit. So it's a little bit negative. On this end, it's a little bit positive. So when we have a cation in solution, the little bit negative end is going to be oriented toward that ion. When we have an anion in solution, the little bit positive ends are going to be oriented toward the anion. Now, the whole hydration thing is a really vast subject to talk about, and really, in its own right, pretty darn cool. But it's beyond the scope of this course to talk about the different spheres of hydration that occur around each of these ions. But suffice to say that a cation gets solvated by the negative end, and an anion gets solvated by the positive end. It is this attraction between the negative end of the water molecule and the positive ion, and the positive end of the water molecule and the negative ion, that allows for soluble ionic compounds to actually dissolve and separate into ions. So how do I know if I have a soluble ionic compound? Well, that's a great question. You could grab a whole bunch of different compounds and try and test them out and see if they dissolve in water. But we've done that for you. So we have the solubility rules. These are for aqueous solutions. There's just a handful of rules, and they will cover about 99.9% of everything that you're going to run into in this course, and really in most everything. So these are things that need to be committed to memory. In other words, you need to memorize them. They are going to be important not only for you to determine what's going to be a soluble ionic compound, but it is going to be absolutely crucial to know these when you are trying to determine the products of some of the reactions we're going to be talking about. So, let's start off. All nitrates are soluble. It doesn't matter what it is. Every nitrate is soluble, as are all acetates. Now, if I want to find something and I want to dissolve an ion, a cation, I'm going to look to see, well, do I have its nitrate or its acetate? Because I know those are always going to be soluble. Additionally, all group 1A and ammonium compounds are soluble. So, if I have a particular anion I want to get into solution, I'm going to see if I can find its sodium or potassium salt, because I know those are going to be soluble. Most halides are soluble except for silver, lead 2, and mercury 1. Remember, what are the halides? These are our group 7A anions. Most of them are going to be soluble. But if you encounter a silver halide, a lead 2 halide, or a mercury 1 halide, these will not dissolve in water. Additionally, most sulfates are soluble, except for silver, the heavy group 2A, mercury 1, and lead 2. So things like calcium sulfate or barium sulfate, these are our heavy group 2As. Those are not going to be soluble. Our mercury 1, lead 2, and our silver. Look, these are very common. For example, silver, lead, mercury 1 were seen in our halides as well. Most hydroxides are insoluble, except for group 1A, calcium, strontium, and barium. Okay, those guys are soluble. How do I know those guys are soluble? Well, the group 1A and the heavy group 2A hydroxides are my strong bases, so they must be soluble. There are some more rules in your book. For example, sulfides. They talk about most sulfides are insoluble except for group 1A sulfides. Well, it's because everything that's group 1A is going to be soluble. These are kind of a condensed bit of rules. And as I said, these will get you through most everything you need to know. Alright, now let's talk about our reactions. As I said, this was reactions and aqueous solutions, but it really should be called reactions, aqueous solutions, and a bunch of stuff that I didn't know where else to put in the chapter. So here are our reaction types. We're going to be talking about these types of reactions. We're going to talk about combination or synthesis, decomposition, combustion, single replacement, double replacement, and redox. Now notice, really, the in solution portion especially talks about single replacement and double replacement reactions. Now, why do we deal with those guys in solution? Why is that most important in solution? Because these reactions require ions. Okay? And in order for us to have free ions, we have to be in solution. So those are really our aqueous reactions. Not that the other reactions can't occur in an aqueous environment, it's just that the ones that are specifically aqueous are going to be single replacement and double replacement. Okay, so for our first reaction, combination or synthesis reactions, these are two or more things that combine to form one. We have a typical reaction style, and you're going to see these throughout all the different reactions, where I have A and B. Okay, now, if I take A and I take B, I'm going to make one thing, AB. So, examples of this might be like magnesium plus oxygen. When you burn magnesium in air, you get magnesium oxide. Or when you take aluminum and you add chlorine gas to aluminum, you're going to get aluminum chloride. These guys, you can see, I am taking two elements and combining them to form one product. It doesn't always have to be elements. But the most common style you will see is the elements. Additionally, there is one that I consider to be very important, and that is the reaction of hydroxides and carbon dioxide. This is important because this is how scrubbers in the space station work, or under the water in submarines. Lithium hydroxide combines with carbon dioxide to form lithium hydrogen carbonate. Notice these guys are special. So anytime you have a group 1A hydroxide and carbon dioxide, you are going to make the hydrogen carbonate. Okay? Now, to determine the products of these guys, I follow my rules for ions. So how do I know that the formula for magnesium oxide is MgO? Well, I know that magnesium is going to be a 2 plus, oxygen is going to be a 2 minus. So it's 1 magnesium to 1 oxide. I know aluminum's got to be a 3 plus, chlorine's a 1 minus, so AlCl3. So unless you have the hydroxide and the carbonate, you need to deal with the ion charges. Okay, so that is combination or synthesis reactions. Two things combine to form one. Decomposition, on the other hand, is the opposite of synthesis. One thing goes to many. So here we have AB goes to A plus B. Now, a lot of times, you're going to have things like compounds forming elements. It does not always have to be compounds forming elements. So, for example, if I heat up lithium carbonate, I can get lithium oxide and carbon dioxide. Or if I heat up potassium chlorate, I can get potassium hypochlorite and oxygen. These guys are often tough to determine the products. Okay? There aren't going to be very many decomposition reactions that I ask you to predict based on just giving you, hey, this is being done to this. So what we need to do when we deal with decomposition reactions, we oftentimes have to look for other chemical clues. And you will see this in the lab, that you are looking for specific chemical clues when you're dealing with decomposition. Combustion reactions. Combustion reactions are technically anytime you have an oxygen reaction that produces heat and a flame. So the typical combustion reactions we talk about involve hydrocarbons. Hydrocarbons are compounds that contain carbon and hydrogen almost exclusively. So the typical reaction style is CXHY, where X and Y are the number of carbon and hydrogen atoms present, plus oxygen forming CO2 and water. This is what we call complete combustion. Okay, complete combustion, you form CO2 and water always. So anytime you have a combustion reaction, it's complete, you form CO2 and water. So some examples here would be like the reaction of ethane with oxygen to form CO2 and water, or the reaction of methanol. So burning methanol, you form CO2 and water. These are complete combustions. Incomplete combustion is difficult. This occurs when there is not enough oxygen present to achieve complete combustion. This is the reason we have carbon monoxide detectors in our home. Instead of producing CO2, they produce CO and water. So, CO is a poison. It binds really, really well to the hemoglobin in your blood cells and does not allow oxygen to bind reversibly to hemoglobin. So basically you suffocate to death with CO poisoning. This is why you don't burn things indoors for long periods of time. This is why they say on gas grills or charcoal grills, do not use indoors, because you're going to always produce a little bit of carbon monoxide when you are dealing with real life size fires. In the lab, most fires are going to follow the complete combustion scheme, though. Alright, our first single replacement reaction. This is our first one that has to be done in an aqueous solution. This is when we have an element reacting with a compound to form a new compound and a new element. So A plus BC goes to AC plus B. I always like to do single replacement reactions in terms of Well, relationships. A single replacement reaction is like you and your significant other go to the bar and they meet somebody better and leave with that person, leaving you all alone. So here you are with your significant other, here you are leaving alone. So the element and the compound form a new compound and a new element. So zinc plus copper nitrate forms copper and zinc nitrate. Or sodium reacts with water to form sodium hydroxide and water. In this case, we can think of water as HOH, whereas I take off this hydrogen as my B there, and then this is my C portion, this hydroxide. So you can see that I go from A with B, C to A, C plus B. Okay? So compound plus an element form a new element and a new compound. These are ionic style. In other words, we're dealing with ions. Now, how do I know if this occurs? In order to tell if a single replacement reaction will occur, we need to take a look at the activity series or the electrochemical series. This number one will always be given to you. This is not something you have to memorize. But the way we use the activity series is pretty simple. The metal above displaces the ion below. Metal above displaces ion below. So when we had our zinc plus our copper 2 nitrate, the metal above displaces the ion. This is the metal. This would be the ion. Zinc is right here. It is above. The copper would be down here. The metal above displaces the ion below. So if I put copper plus zinc nitrate, would this reaction occur? The answer is no, because the metal has to be above the ion. In this case, the zinc ion is above the copper metal. So always use the activity series. The metal above displaces the ion below. Our next reaction, double replacement, metathesis, yada yada yada. There's a bunch of different names for this. If there are a bunch of different names for this, this must be a very important style of reaction, and indeed it is. Now, this is when we have two aqueous ionic compounds form two new compounds, okay? And one or more is usually a solid, liquid, or gas, okay? So you're going to get a solid, a liquid, or a gas. That is the driving force for the double replacement, metathesis, gas-forming reaction, acid-base reaction. That's what we call these guys. The typical reaction style is AB plus CD goes to AD plus CB. So this is you and your significant other go to a bar, you find a couple, and you leave with each other's partner. So it's the swingers reaction. Now, I know that seems really funny, but I have never had anybody forget what a double displacement or a double replacement reaction is by calling it that type of reaction, by talking about it in terms of relationship. So don't be offended. It's just a way to help you remember what's going on. So, for example here, if I have lead 2 nitrate and potassium iodide, I make lead 2 iodide plus potassium nitrate. So here I've got a bunch of ions in solution. How do I know that these ions are in solution? Because I know my solubility rules. All nitrates are soluble. That means this guy is aqueous. All group 1 compounds are soluble. That means that guy's aqueous. Now, on the other side, I actually make a solid. Now, I need to know which solid this is. Is this the lead 2 iodide or is it the potassium nitrate? Well, I know it is the lead 2 iodide because most halides are soluble. Exceptions include silver, mercury 1, and lead 2. This is the lead 2 ion. The lead 2 halide means this guy is solid. So this is lead 2 iodide in this test tube here, that brilliant yellow color. In order to determine your solids, you have to know your solubility rules. This is why It is so important to memorize those solubility rules. So the double displacement is very common. The special cases, or we can call them different things, are precipitation reaction. To determine the products of a precipitation reaction, we need to use our solubility rules. Then we have the acid-base. This is where we're going to form water. Okay, so we're forming a liquid. Remember I said solid, liquid, or a gas. Acid-base is water formation. And then we have our gas-forming reactions. And these are going to occur when we have sulfites, hydrogen sulfites, carbonates, hydrogen carbonates, and sulfites. These are going to react with acids. Okay, so I'm going to talk about these in just a second. But first, let's talk about what an acid and a base really are. I know I've used those words before, and you've used them before in life and in the lab. But let's talk about what we mean by acids and bases. Well, our acid-base theories really hinge on three different theories of what an acid or a base are. And matter of fact, acid and base chemistry is actually one of the main foundations of all chemical reactivity. So, what is an acid? Well, first definition we're going to have is what we call the Arrhenius definition. This was named after a guy named Svante Arrhenius, and what he did was he was dealing with electrolytic solutions. He would pass electricity through them and studied all sorts of different things with electrolytes. One of the things he did do that we do not do today is he actually tasted his solutions. And he proposed that an acid is a substance that dissociates into hydrogen ions in water. So something like hydrogen chloride. It dissociates into H plus ions and Cl minus, what we call hydrochloric acid, or HC2H3O2. This is acetic acid. Now, acids are corrosive. They eat metal and they will burn the flesh. But particularly, acids tend to eat metal. Okay? Now, what really occurs is not that it actually forms an H plus ion, because think about what an H plus ion is. Hydrogen is the simplest element. It's only got one electron. If I take away that one electron, all I'm left with is a bare proton. We don't think that a bare proton really exists in solution, because it's just, you go to make something way too small. So what we actually think is there's a reaction where the water molecule actually will take on that hydrogen ion and form the hydronium ion. So whenever we have an acid in water, we're really forming the hydronium ion. Now for bases, Arrhenius said a base is a substance that produces hydroxide ions in water. Things like sodium hydroxide, potassium hydroxide, magnesium hydroxide. These are caustic, which means they eat flesh. Now, what we really have when we have the hydroxide ion in water is just simply the hydroxide ion in water. That is the base. Now, the hydroxide ion wants to grab another hydrogen to form water, which is the way that acid-base reactions occur. Now, what we have here in the picture is actually something that's going to be more easily explained using the next definition. But this is when we have ammonia and we put it in water. We can think of this occurring where the ammonia molecule is going to grab a hold of one of the hydrogens off of the water molecule and form the ammonium ion. And what's left after you pull off a hydrogen is the hydroxide ion. So that's one way we can think of it. Now, the best way we can think of this is in terms of the next theory, and that is Bronsted-Lowry. The Bronsted-Lowry definition, and really this should be Bronsted-Lowry, an acid is a proton donor. Now, this means we still need an ionizable hydrogen atom, just like the Arrhenius. So the Arrhenius and the Bronsted-Lowry definitions of an acid really don't change much. What does change is the concept of the base. An Arrhenius base required the hydroxide ion, but a Bronsted-Lowry base is a proton acceptor. So anything that can add a proton to it, which means you need an extra unshared pair of electrons. Anything that has that ability to add an extra H plus can be a base. So for example, water acts as a Bronsted-Lowry base. Remember we talked about what happens when we put an acid in water, we really add that extra hydrogen atom to the water to form the hydronium ion. That's actually a Bronsted-Lowry base reaction. Hydroxide, again, is a Bronsted-Lowry base because if I add a hydrogen to it, I get water. And ammonia, as we talked about just a few seconds ago, can add an extra hydrogen to form the ammonium ion and the hydroxide ion. So these are the Bronsted-Lowry. An acid is a proton donor, and a base is a proton acceptor. Now I have one more definition of acid-base theory that is not in your book. However, I like to teach it because I can show how the rest of chemistry relates based on this next definition. So, Arrhenius acids and bases gave us a pretty basic definition. Basic, no pun intended. A simple definition. Bronsted-Lowry actually gave us a little bit more nuanced idea of what a base is. This next concept, Lewis acid-base theory, really expands what an acid could be. So, in the Lewis definition, an acid is an electron pair acceptor. Okay? So this is anything that is electron poor. This explains why transition metal cations are acidic in solution. They are deficient of electrons. And a base is anything that has an electron pair donor. So really, this is like a Bronsted-Lowry base. Anything that's electron rich, it has the ability to accept an H+, must be electron rich. Therefore, it is a Lewis base. Alright, in light of those acid-base definitions, let's talk about our specialty double displacement reactions. So first we had the acid-base reaction. This is going to form water. Now, when we deal with an acid-base reaction in this class as a double displacement, we're really going to be looking at specifically an Arrhenius acid-base reaction. Okay? So, an Arrhenius acid like HCl plus an Arrhenius base like NaOH will form sodium chloride and water. Really, you can see that this is a double displacement reaction. AB plus CD goes to CB plus AD. Now, you might say that doesn't look like AD, but remember, we can write water as HOH. So, we can see that that's very similar to our double displacement. Now, the key here is we form a salt and water. Acid-base reactions will always form a salt and water. Now, this is sodium chloride, which we consider to be the salt. That's a salt that we always eat, right? But a salt is simply an ionic compound. Okay? That's what we term a salt. Most often a soluble ionic compound. But it could be something like HCl plus KOH, yielding KCl plus H2O. This is our salt. Okay, so a salt and water. That's always the products of an acid-base reaction for us. The next reaction we're going to talk about is when we have our gas-forming reactions. Our gas-forming reactions are going to be when we have sulfites, SO3 2-, hydrogen sulfites, HSO3-, sulfides, S2-, hydrogen carbonates, HCO3-, and carbonates, CO3 2-. These are going to react with an acid. Okay? So let's do the carbonates first. Let's deal with HCl plus NaHCO3. So sodium hydrogen carbonate plus HCl, hydrochloric acid. If I just take this as a double displacement reaction, and I do the AB plus CD, what I would end up with is something that looks like this: NaCl plus H2CO3. Now that would be perfect if there wasn't a slight problem. H2CO3, carbonic acid, is unstable and undergoes a decomposition reaction to form water and CO2. This is our gas, okay? The gas in our gas-forming reactions. So, whenever I have an acid plus a hydrogen carbonate, I'm going to make my salt, but I'm going to make water and CO2 here, okay? So this is for hydrogen carbonates and carbonates. I'm going to make water, CO2, and my salt, okay? Now this is different than if I have my sulfites, okay? If I take HCl plus NaHSO3 and do this double decomposition style, double displacement, I don't know why I keep saying that, double displacement style, I'm going to make NaCl plus H2SO3. Now this is sulfurous acid. Sulfurous acid is also unstable and will decompose into water plus sulfur dioxide gas. So if I have a hydrogen sulfite, or a hydrogen sulfite, or a sulfite, and I add an acid, I'm going to make my salt and water and SO2 gas. Okay? So hydrogen plus a sulfite, a hydrogen sulfite, I make a salt, water, and SO2 gas. Okay? Now, the last one we're going to talk about is the sulfide. Now, the sulfide is slightly different. The sulfide ion, whenever I add an acid to the sulfide ion, so something like HCl plus Na2S, I'm going to make H2S plus NaCl. So I make my salt still, but I make hydrogen sulfide gas. Hydrogen sulfide gas is the smell of rotting egg. So this is not a very happy smell to be smelling in the lab. So sulfides plus acid gives me my salt and hydrogen sulfide gas.